Look closely at this landscape. For decades, the moon was treated as a finish line. Today, it is a starting line, a massive physical reality sitting in our cosmic backyard that holds the raw materials necessary to move human infrastructure into deep space. Escaping Earth is expensive. Every kilogram of cargo launched into orbit requires an enormous amount of chemical energy to break free of Earth's gravitational pull, a physical barrier known as the gravity well. The moon offers a mechanical advantage. With only 1/6 of Earth's gravity, launching heavy, processed payloads from the lunar surface requires a fraction of the fuel. It functions as a logistical springboard for interplanetary missions. To use that springboard, we have to stop dragging supplies up from Earth. The rockets, the habitats, and the fuel must be built on site, using the resources locked inside the lunar crust. That is the problem a coalition of government agencies and private aerospace companies is currently engineering a solution for. Between 2026 and 2032, organizations like NASA, SpaceX, and Blue Origin are launching a campaign to prospect, extract, and refine these extraterrestrial materials. We are watching the transition of the moon from a barren rock into a resource-rich foundation for a permanent human civilization. At the lunar South Pole, the geography creates deep depressions where sunlight never reaches the floor. Inside these permanently shadowed regions, the temperature drops to 200 degrees below zero. Trapped within this darkness are ancient deposits of water ice, preserved over billions of years. Through a process called In-Situ Resource Utilization, engineers can purify this ice for drinking water, or electrolyze it into hydrogen and oxygen. This provides breathable air and rocket propellant on site, removing the weight and cost of launching those supplies from Earth. Extracting it presents a scientific dilemma. Researchers warn of a polar ice paradox. This ice contains a 1.5 billion-year-old record of the solar system, and mining it for survival could erase irretrievable historic data. Despite the risk, water remains the most valuable short-term resource. It provides the life support crews need and the fuel that will propel them further into the solar system. Away from the poles, the vast basalt plains of the lunar seas hold a different kind of wealth. Embedded in the rock is a multi-component mineral called ilmenite. Through intense heat, ilmenite ore separates into iron, breathable oxygen, and metallic titanium. Robotic 3D printers will then use this refined titanium and lunar dust to build reinforced walls deep inside underground lava tubes, protecting crews from cosmic radiation. To run these massive printers, the bases will need power. Silicon, stripped directly from the lunar dirt, will be used to manufacture local solar arrays, establishing a sprawling energy grid. That same power grid will energize communications. SpaceX is adapting its Starlink technology to build Moonlink, a dedicated satellite constellation orbiting the moon to provide high-speed broadband directly to surface operations. By turning native rock into shelter, power, and bandwidth, the moon effectively functions as a self-sustaining industrial zone. Operating advanced technology in a vacuum requires complex electronics. The raw ingredients for those systems are concentrated in unique lunar rock formations, known as creep, concentrations of potassium, rare earth elements, and phosphorus. These rare elements power modern computing. They are vital for manufacturing semiconductors, for building precision optical sensors, and for advanced terrestrial defense systems. Securing these elements guarantees an uninterrupted supply chain for both the expansion of lunar colonies and the high-tech industries driving the global economy. If titanium provides the skeleton of the lunar base, rare earth elements provide the marrow, the internal intelligence running every rover, server, and life support monitor. Without an atmosphere, solar wind bombards the moon, embedding a rare isotope called Helium-3 into the dust. Scarce on Earth, the lunar regolith holds thousands of tons. Valued at $20 million per kilogram, it is the space race's primary economic prize. It is highly coveted as a critical coolant for quantum computers and as an ideal fuel for next-generation nuclear fusion reactors. Private startups like Interloon and Blue Force are already developing specialized tilling machines designed to excavate the lunar topsoil and harvest the isotope before competitors arrive. Extracting helium-3 promises a sustainable, high-yield energy source. It is the fuel intended to power the lunar economy and eventually propel heavy spacecraft toward Mars. The execution of the strategy begins in 2026. Robotic modules like Blue Ghost and Griffin Mission 2 will descend to the lunar surface to map the terrain and test exactly how rocket exhaust erodes the topsoil. Lifting these heavy payloads requires brute force. Vehicles like the Falcon Heavy generate over 5 million pounds of thrust to send landers on a direct translunar trajectory, returning the side boosters to Earth to keep costs low. The permanent colonization phase relies on the Starship human landing system. This vehicle is designed to deliver 100 metric tons of infrastructure straight to the lunar South Pole, providing the volume needed for long-term habitats. Behind these payload capacities are thousands of engineers actively fabricating the hardware. The clean rooms are full, and the metal is being cut, welded, and tested for imminent launch. The lunar gold rush is no longer theoretical. The hardware is physically being built and shipped to the launch pad right now. The rockets standing on these launch pads are the first operational links in a permanent extraterrestrial supply chain. If the testing phases of Artemis and Starship succeed, they will provide the high-volume transport capacity required to maintain a presence on 2 worlds simultaneously. There is a distinct beauty to a species that looks up from its own flaws, asks how the universe works, and builds the bridges to go find out. The drive to mine, explore, and expand reflects a fundamental human curiosity. By reaching for these resources, we are extending the reach of consciousness further into the cosmos. When humans return to this dust, we are not going as visitors. We are transitioning into permanent residents of the solar system.